In this video lecture, we discuss about another extension of the least square problem. It's in the direction of scenario that some problem parameter of least square has some uncertainty. This is the ordinary least square problems. All right, you have A, you have B, you minimize the two norm of the residual. But now in this situation, we have some uncertainty on A and B. These come from the practical point of view that probably your regressor matrix A, right? Usually the regressor matrix A contain the measurements that you observe from the sensor. Is a measures of physical variable that's supposed to be predictors of your model. Okay. And also the vector B, the meaning of the vector B is the measurements of the response variable. Again, yet if you have some idea that this B is uncertain, probably in probabilistic sense or another kind of sense, now we're going to propose a framework that is robust to this kind of uncertainty. The way we will handle this uncertainty can be split into two categories. The first one is that the uncertainty on A can be viewed as, A belong to some uncertainty set. This set has, a lot of members, a lot of possible combinations of different values in A. But in the first direction, we assume that A is deterministic, is not random. In the second case, A is assumed to be random. So it means that in the second case, you model uncertainty in A by using the concept from from a random variable and stuff. In this video clip, we will focus on the first direction. Okay. In this direction, we sketch that A belong to a set, calligraphy A. This is called uncertainty set. Okay, this set is a subset of Rm by n. The matrix A has size m by n. What we're gonna do is the following. So this is the uncertainty set that has a lot of members in there, like A1, A2. Okay, the member can be infinite numbers, all right, or it can be finite. But the thing is, your choice of A is just one member of them. Okay. What we're gonna do is that in practice you don't know exactly what the values of A. What we do is we measure the true norm of the residual. But because A is uncertain, what we do is we take the supremum of the true norm of the residual, and that is the supremum over A. Okay, why do we take the supremum? It means that you pick one A. Okay, suppose I index with A1. Okay, you measure the true norm. You pick another A. All right, suppose it's A2, and you measure the norm. Of course, the norm one, let me use the norm. Let's say I use the values of as Z1, Z2, and if you can, it depends. If the member is finite, maybe you can measure all of them. All right, you can measure all of them, and then you're gonna take the supremum, which is basically a maximum of the true norm. Now you're going to take the supremum across A over all possible choice of A in this uncertainty set. This is called the worst case norm because you take the supremum. And when you take a look at this expression, you take the supremum over A. The result of this is going to be a function of X. Okay, when you take the supremum of the two norm here, you can think of x and y as fixed, as given. All right, and as you vary the choice of the matrix A from the uncertainty set, which A is going to give you the worst case norm. All right, that is the process of taking supremum over A. But once the supremum is calculated, the result is, of course, is regarded as a function of x, and then you minimize over x again, right? So what you do is actually you minimized the worst case norm, okay? And this framework is called the robust least squares. From the lecture of convex optimization problem, we have this property that now you take a look at this as a function of a and x, right? As a function of two variables. The function f is convex in x, right? It's convex in x for each fixed a. Okay. So we have these results that is a supremum principle. So when you take the supremum over A, when A belongs to some set calligraphy A, this set A doesn't have to be convex or anything. The result as a function of G, this G is still convex. Okay, so all the assumption you need is that that function is convex in X. And if you take a look at f Ax as the norm of Ax minus y, right? That is a two norm of composite, is a two norm of fi function in X, so it is convex in X. All right. So in conclusion, the formulation of worst case robust least square given by this problem is always a convex problem in X. How are we going to solve it? Because what is the expression of Gx exactly? That depends on the description of the uncertainty set A. And now we're going to give you by some example, all right? Because it's the tractability depends on the set E. Now, I have the set uncertainty set A that described by this. It described by a nominal value of A. I use the notation A bar. Is the nominal value plus some uncertainty. All right, plus some uncertainty. And the uncertainty is varied by some sense, but I control the size of the uncertainty using the Frobenius norm of E. Okay, so my matrix A is decomposed as A bar and the error term, but at error term, I control the size, the magnitude of the error term by using the Frobenius norm. Okay, so the parameter, the scalar small e is given by the user. Okay, in that sense, all right, it means that, remember the matrix A, this is called regressor matrix or the sensor matrix. It means that your sensor has some, has some variation, is controlled by the nominal value, okay, and the error term. When we use the Frobenius norm is just the two norm extended for matrices. So when you say that the Frobenius norm is bounded by E, it has a sense that, okay, you are given by the RMS, the root mean square of the error term, where the error term represents the noise occur in the sensor. Okay. Now, what I'm going to do is I'm going to calculate the two norm, the worst case norm. The first step is this. Okay. Now I'm going to start by the two norm square, right? So Ax minus y is going to be, I'm going to plug in A bar plus E x minus y. and that is A bar X minus Y plus EX. So I'm gonna, to shorten the notation, I'm gonna call this guy W. All right, because at the process of computing the worst case norm, X and Y, A bar, these are known and fixed, right? The nominal values of A is supposed to be known, supposed to be fixed. So I call this guy W instead. All right. The next step is I just expand this quadratic form, just regular expansion. And then I'm gonna find what I'm doing now is that I try to find the supremum over A. So to find the supremum, first I try to find an upper bound. Okay. When I see an upper bound and I try to show that, oh, that upper bound can be achieved, can be attained by some choice of the the variable, and that's supposed to be the variable E in here, because my A again is A bar plus E, right? If I take the supremum over A, it's going to be the same as I take the supremum over E. Okay, so that's why the whole process I'm gonna present shortly is going to be like, okay, I find the supremum over E by showing an upper bound first, and I will try to show that that upper bound can be achieved by a specific choice of E, and that is a choice that leads to the worst case norm. Okay. Next, the next process is purely, results from linear algebra. First, I would like you to take a look at the quadratic form in X that is bounded by the lambda max of E transpose E times the norm square. Okay, I hope you review. This is basic, right? This is quadratic form in X. This is some matrix B, all right, that is bounded by the lambda max. Okay, the second term here, this is your homework problem. Because W transpose EX is actually the same as the trace of W transpose EX, right? Because this is a scalar. So scalar equals to the trace of itself. But then you can use the trace property, the circular property, that say I can move X around to the front, all right? And then, of course, I know that this is circular property, and then I write it as trace of WX transpose E, okay? So that I can take a look at this as another matrix, let's say B. So that's the second term. Next, the second inequality, I use the fact that the lambda max of E transpose E is bounded by the Frobenius norm of E. Again, yes, it is not difficult to see. Please check, all right? Because let me mention real quick that the Frobenius norm of E is the trace of E transpose E, right? What is the trace of a matrix? What is the relation of the trace of a matrix with the eigenvalues of that matrix? Can someone answer? What is the trace of B and the relation with the eigenvalue of B? Sitipap, Ping, Lim, anyone? Napat? Sitipap?
It is the sum of eigenvalue of B.
Very good. Trace of B is a summation of the eigenvalues of B. Okay, think about this. So the trace of E transpose E is supposed to be the sum of eigenvalue of E transpose E. Okay. And now try to think about this relation. Why the maximum eigenvalue of E transpose E is bounded by the Frobenius norm. Okay. Not hard, right? As you see this relation. Next, the yellow term. The yellow term, I'm gonna apply the Cauchy-Schwarz inequality for matrices, because here in the yellow term, I already have in the form the trace of B transpose E. Okay, so this is Cauchy-Schwarz. Next, in the last line, because I from the description, the Frobenius norm of the error term matrix E is bounded by E. So here you have E squared. Okay, and then the yellow term, I apply that the Frobenius norm of F of E is E. Okay, and the Frobenius norm of W transpose, WX transpose is the same as the norm of the two vectors. Okay, please verify the steps in between. So once I have an upper bound, I can complete the square. All right, that is the norm of that is E times the norm of X plus the norm of W, everything squared. The most important step is this. Now we have achieved some upper bound of the residual error. This is some upper bound. All right, your true norm of the residual error is here. You get some upper bound. But then the supremum, to show that the supremum is this upper bound, you need to show that supremum can be attained, can be achieved by some choice of E. All right, some choice of E. And now it's not hard to verify that choice of E is given by the outer product between W and X, where the choice of scaling alpha is given by this. This is in your homework. Please verify. Okay. So when the worst case norm is attained, all right, now you can say that the supremum is given by the right hand side of the equation 3, equation 3, and then you just plug in the form that W, you define W to be A bar X minus Y, right? So that is A bar X minus Y, the true norm here, plus E times the true norm of X. Okay. So this is how you derive the supremum, the worst case norm of the residual. And then you see that the next step is, of course, you're going to minimize over X, A bar X minus Y. Okay. I mean, in the other steps in between, I didn't put specifically what norm I use, but I mean, I would like to know that it's all the two norm. But I mean, to avoid the subscript and everything, which is annoying, I leave it as a norm. But this is not any norm, right? Okay, this is two norm. Again, when you take a look at the results, the robust least square is a convex problem because it's a sum of two norms. In optimization point of view, let me remind that this is not the same. What we derive is not the same as the sum of two norms squared. No, it is not. Okay, what we derive is a sum of two norms. It is still convex, but it is not quadratic problem. From optimization point of view, this is called second order cone programming. But I mean, you don't need to worry about this problem type right now. Okay, it will be more discussed in optimization class. But take a look at the result. When it hit 9:30, I'm gonna finish the slide until page 22. So anyone that has to leave, you can leave. But I'm gonna record until the end of the lecture. Now let's take a look at the result. What I do is, okay, I generate A as the nominal value plus some error. Okay, the error term I generate randomly, but I control the size of the error to have Frobenius norm as 0.1, small e. My nominal values is fixed, is deterministic, has a size of 20 by 5. RLS is the robust least square formulation. Okay. So robust least square is the formulation that I solved from this problem. Okay, second order cone programming. Actually, we can use CVX as well because I mean, you can use this as a modeling software so that you don't need to worry how to solve second order cone. For now, we can also consider 3 cases of the least square. Okay, if you don't have to for robust least square, now you can maybe think heuristically that okay, in the least square, if you use least square, of course, probably I use a bar, the nominal value. That makes the most sense. Use the average, use the nominal value to compute the solution. So that's one possibility of the least square, of applying least square to these uncertain problem. The second choice is that when I have information that my A is uncertain, okay, and I know that the size of uncertainty is 0.1, that's the Frobenius norm, okay. But then you can think of, okay, maybe I use A bar minus delta, okay. Like I think of this should be a kind of the values of A on. So suppose my A bar is here, A bar minus delta is here, A bar plus delta is here. I try to use the extreme side of my A, but it's the extreme side to the left. Okay. So, and maybe I heuristically use delta around 0.01. Okay. And then another case is I use the A bar plus delta, the extreme side of my uncertain A on the right hand side. Okay, this is a least square, all right? So which means I solve A bar x minus b, I solve A bar plus and minus delta x minus b. I get 3 solutions. And then I compute the worst norm, all right? I compute the worst norm. The worst norm is given by this expression. Okay, it's given by this expression and with the parameter e, so I can vary e from 0.01 to around 0.5. And then as I observe the actual worst norm, all right, we will see that the robust least square, which is the blue bar, you see the worst norm tends to be robust to the size of the uncertainty. Unlike least square, when the uncertainty degree is at minimum, is small, you don't see the difference between robust least square and the least square. But as the degree of certainty is higher, you see that all the 3 bars that refer to the least square, ordinary least square problem, the worst norm is very sensitive to the degree of uncertainty. All right, that's the worst norm. In the top bar, I do the same, but now I pick any solution x, not solution, I mean I pick the values of x. I pick the values of x randomly, and I compute the worst norm. Again, yet I use the expression of the worst norm in here. In the top bar, I try to express that if you just pick x randomly, not from a solution to any kind of estimation problem, you will see the variation of the worst norm, right? Some choice of x has small worst norm. Some choice of x has high values of worst norm. And the variation here is very big, regardless of the values of e. Okay, so that is the information. That is the conclusion that using the worst case robust least square, okay, it has a benefit that when the uncertainty degree is large, your solution is gonna robust to that uncertainty. Okay. Next, I would like to give some example. Okay, I would like to make to the point that in this example 1, we have description of the uncertainty A in this way defined by the forbiddance norm of the error. You put kind of a linear additive structure of the uncertainty in A. Okay, I would like to make this point by giving you the second example that the tractability of the problem depends on the description of A. We will get to different mathematical formulations when the set of uncertainty now change, okay, as in the second example. In the second example, I also consider the linear additive structure of A, which means my A is still nominal value plus uncertainty. But now I describe the uncertainty matrix in different way, different from the example 1. Now I would like to use the notation that my U, which has the same size as A, okay, has ij entries, has ij entries, and the modulus, the magnitude of uij is bounded by aj. Okay, my u is going to be u1, u2. It has n columns, all right, and then my j column has u1j, right, u2j, umj. Okay, all the entries here, all right, is less than aij, to be precise. These correspond. Remember that when you have a matrix A, A bar plus U bar, remember again that each column of A represents measurements value of a predictor of an input variable. So when you have the constraint that each columns of U, okay, each columns of U, all the entry in a certain column of U has a modulus, has a magnitude of less than aj, less than a scalar. It means that you allow, the sensor of one physical variable to have a certain value of variation. Okay, in this sense, now the point of this slide is to show that how can you compute the worst case norm. Okay, we do the same process. We write, we consider ax minus y, but your a is a bar plus u x minus y, and that is a bar x minus y plus ux. Okay, now you call this constant. It's constant for the moment. For the moment when we compute the worst case norm, we call it w. Okay, and now, so taking the supremum over a on the w plus ux, right, is going to be the same as taking the supremum of w plus ux, but now you can take the supremum over u. Okay, so I would like to use the blank page, right, to calculate this w plus ux, okay, where your u is u1, u2, un, all right, and the size of your uij, okay, is always less than aj. You take a look at each column of u again. All the entries in the column j is bounded by aj. Okay. Now what you're gonna do is the following. The true norm of ux plus w plus 2x ux. Now, okay, I will sketch a note again. Your u has n columns, so ux is going to be u1x1 plus u2x2 dot 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 unxn. All right. So ux can be written as the linear combinations of n columns in u. So it's going to be w plus u1x1 plus u2x2 dot 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 unxn. Now, again, what we're trying to do is find the supremum over u, or find an upper bound of these two norms. The first inequality to find the upper bound is to apply triangle inequality of a vector. Triangle inequality is to say that this is bounded by the norm of w plus the norm of u1x1 dot 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 the norm of unxn. Okay, but here in this expression, I would like to note that xk is just a scalar. Okay, so it is 2 norm of w plus absolute value of x1, the true norm of u1. All right. The norm of alpha uk is going to be absolute value of alpha times the norm of uk. That is the property of norm. So you have this. All right. Of course, you would see this as what? As the true norm of w plus what? It looks as if the sum of xk times the norm of uk. This is just try to write it as a summation. But then again, when you have a summations of two guys like AI and BI, right? You can think of this as the inner product between A and B. Okay. All right. So then I'm going to change a little bit. I'm going to change the notation. So you can think of this summation as like you have a vector that contains magnitude of x1, the magnitude of x2, dot, 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 magnitude of xn, right? And now another vector is a vector of what? The true norm of column 1 of u, the true norm of column 2 of u, dot, 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 column to normal column n in U. Okay. Now now what I'm gonna do is what? And what I'm gonna do is what? Okay. What about of course when I take the true norm of, okay, now I'm considering the UK, the column K of U. So I have U1K, U2K, dot dot UMK, right? Because I have the M entries. So when I compute the two norms, so it's gonna be bounded by the root m of the infinity norm of the vector uk. So this is some relationship between two norm and infinity norms. Okay, but the infinity norm of uk, what is the infinity norm? The infinity norm is to take a look at each entry and take the maximum magnitude, right? So that is bounded by the given information that is given by AJ. Okay, that is given by AJ. Again, I use this information, this inequality about the norm. Check out the the relationship between two norm and infinity norm. All right. Now, now you're gonna have that the two norm of each column in U is of course bounded by A1, A2, dot dot dot, AN. All right, with the factor of square root M. Now I'm gonna replace. Okay, so what I'm going to do here is that I'm going to use vectorize the vector notation. So this is going to be bounded by the two norm of W, okay, plus plus the factor square root M that we see here, and A transpose magnitude of X. All right, so I call these, I use the notation as magnitude of the vector X, but what I mean is I take the magnitude of all elements. Okay, so the bound here is given by the vector A. The vector A contains AJ. Okay, so it can be shown that this is an upper bound of the worst case norm. Now we would like to make a point that, okay, how we can achieve this upper bound? When does the supremum occur? Now we need to go back a little bit when we first obtained the first inequality. That is the triangle inequality. So I mean, you have the sum of several vectors. The norm of the sum is bounded by the sum of the norm, but it's not hard to see that. Let me pick a note here. If you have a sum of two vectors, of course, the triangle inequality says that is bounded by the sum of the norm, but it is equal. Think about when they are equal. They are equal when x and y are parallel, when y is a multiple of x, right? Please verify. Then we can apply this result, which means when we get the step here, when we apply the triangle inequality, it becomes equality when when each of ui is supremum occur. All right, when all the ui is in the direction, is in the same direction as w. All right, so what I'm going to do is, okay, I try to represent that it's in the direction of u, so I normalize the vector w first by its two norm, and I put some scaling alpha. Okay, and of course what alpha would be? What alpha would be? My alpha would depends on the my alpha would depends on the restriction that my all the entries in the column ui has to be bounded by aj. Okay, so I put alpha I to know the index I here. So my alpha I is supposed to be somehow related to AI. So try to think about it. All right. All right. So the point here is that the supremum occur when UI is in the same direction as W. Okay. From this result, now we can go back. Okay, as we see that this is the worst case norm. All right. Then we just put back W equals what? A bar X minus Y. Okay, and then we go back here. We end up at the worst case norm where the choice of the supremum, where the results of this supremum occur when uj is in the direction of W, which is a bar x minus y. Okay, and then if you take a look, so the last result is going to be the minimize of root m a transpose x magnitude of x plus the two norm of a bar x minus y. When we look at this objective again, this is the resulting optimization. Obviously, from the cost objective, this is two norm, this is convex function in x. But now take a look at the first term. The first term is what you do is you take the maximum take the magnitude of the vector x. That is the absolute value function, which is convex, right? And then you make inner product with a, so which is just a scaling. So if you just write it down, it's going to be like sum of ai or xi, all right? So that is, you can think of this as the weighted L1 norm as well. So this function is convex. Again, convex function. What type of convex function? We can show that it's a second order cone programming. Okay. So this is the this is again yet to show that you get you obtain different formulations. In the second case, in the second example, you make use of the upper bound of the matrix U, upper bound of uncertainty. In the first example, you control the size of the variation of uncertainty using the Frobenius norm. Just like Frobenius norm is an extension of the L2 norm. Take a look at the result. The result is you end up with the two norm. This is the extra term from the two norm, the residue. Here you get the two norm of x. So you can think of this as a what? As a regularization problem point of view as well, because it means that when your A is uncertain, you trade off between the error from the nominal values of x, but also at the same time you try to reduce the size of x. This is just like L2 regularization, but mathematically it's different objective functions. So because when you reduce the size of x, it means that you are your x, when you use x as a times x, so that you get x hat, because your a is uncertain. When the size of norm is smaller, when x is smaller, it becomes your y hat to be less sensitive in a, because your a is going to be a bar plus e, right? Because you know that your a is uncertain because of the term e. So whenever x is has smaller norm, it reduces the effect of that uncertainty in e to affect your prediction, you estimate in y, right? Example 1, you use Frobenius norm, you end up with the two norm. In example 2, my point is you use upper bound in the error term. Upper bound is like controlling the infinity norm of the jth column in U. You will see that it is nice to see that the resulting formulation plays a role of L1 penalty. As the same, the concept is the same. The resulting optimization problem is to trade off between residual norm measured by the two norm of the nominal model, but also at the same time you try to reduce the norm of x. But here you use the L1 norm, weighted L1 norm, as a way to measure the size. Okay. So this is the two examples of robust least square using the deterministic approach, which means you try to find the worst case norm when A is uncertain. And then after taking the supremum over A, you minimize X. Okay. The choice of the uncertainty set in A will lead the problem to have different formulations.